everyone. Welcome to today's session of ENERCOMP seminar series. In this seminar series, we highlight cutting-edge research in composite performance and digital solutions.
Then I can introduce myself. My name is Kilian Tschöke. I'm from the Fraunhofer IKTS, which is an R&D institute in Germany. I have also some slides, a few slides just to give an overview. I'm mathematician. I studied mathematics and then specialized in modeling and simulating ultrasonic waves, elastic waves. Really often, or especially so-called guided waves, or also known as lamp waves, in composites, in metal structures, or in sandwich structures, so in really complex geometries. And I'm managing several R&D projects regarding the development of sensor systems, monitoring systems, and non-destructive testing systems for a lot of different applications. So it changes from project to project. I'm not limited to any material or structure. We are focused in developing the monitoring and the sensor system. And I'm really happy that I can give a talk today, to have the opportunity to present some of our research results and to show you current developments for monitoring techniques, especially based on guided waves, for metals, for composites, and for different other applications. Then I'm going to start sharing my PowerPoint presentation. Yeah, again, hello everybody and welcome to my talk. As introduced, it's about monitoring techniques for guided waves. As part of the seminar series here. And these are not only results from my work, it is based on the work of all of my colleagues. They are mentioned here. But if you have further questions, if you want to get in contact with us, then feel free to send an email or to call me. And on the last slide, I will also have my contact details. Yeah, let me start with a short introduction. What is Fraunhofer, or what is my work about? Fraunhofer is a non-profit research organization in Germany. I think it is the biggest R&D organization in Germany. We have 76 different institutes working on different topics, with about, I think now, more than 30,000 people, and then annual budget of more than 3 billion euro. Fraunhofer itself says we are a step between university and industry. So we are not doing basic research or fundamental research. We try to transfer knowledge or to transfer academical results into the market, into the industry, working together with industry partners who maybe do not have their own R&D departments. And we are focused in bringing technology into the market by licensing or by spin-offs, so by founding new companies. And in the end, we are not a competitor on the market. We are a non-profit R&D institute. The IKTS itself, so my institute is called IKTS. That means ceramic technologies and systems. And we are here in the east of Germany. The town is called Dresden. We have 3 different branches. One is focused on material development, especially, of course, ceramic technology, ceramic materials. And if you want to develop materials, you also have to investigate the materials. You have to do material diagnostics, and this is where I'm from. We are an institute for material diagnostics, non-destructive testing, material monitoring, and we are in total 150 people, I guess. 150 people only working on non-destructive testing, monitoring, and material diagnostics. And the others, in total, we are 800 people. The others are working on material development. As I mentioned, our institute here, our site here, is focused on material diagnostics. Our main methods are, of course, optical methods, electromagnetic testing, like eddy current testing for composites. My department, or the department where I'm from, is specialized on ultrasonic testing, NDT using ultrasonic waves. If we permanently install sensors, then we are talking about condition monitoring or structural health monitoring, SHM. We have also departments working on micro and nano analytics, so analyzing nanocircuits and microchips. We are working on the reliability of electronics. That means if we want to embed sensors into a structure or into an application, then we have to assure that this electronics also works reliable for 20 or 30 years. And of course, we also develop bio and environmental technology. Some examples from our house is, for example, the Sarah code, which is a printable QR code for high temperature applications. So with this code, you can mark your products in high temperature manufacturing processes up to several hundred degrees Celsius. From our department, we have a sensor sleeve that you can see on the right side, or let me use the PowerPointer. Here on the right side, you can see the sensor sleeve that is especially developed for offshore and underwater applications, but can be also used for other applications. And we also develop full inspection systems, for example, based on ultrasonic phased array techniques, like testing device for these hollow shafts for the railway industry. All high-speed trains in Germany, the ICE, the high-speed trains, are tested with equipment from our house here. Our department itself is called Condition Monitoring and Non-Destructive Testing Services. The head of our department is Lars Schubert, one of my colleagues, or so to say, my boss. He is also the head of the German Expert Committee in Condition Monitoring, so the German Society of Non-Destructive Testing, the so-called DGZFP. They have different expert committees working on guidelines or standards or norms up to ISO standards. And the expert committee in condition monitoring, the head of this group is my boss, Lars Schubert. And our department itself, our R&D department, is specialized in all components of the value chain. If you want to develop a sensor system, from modeling and simulation, which is mainly my part. As a mathematician, I'm specialized in simulations. We develop the measurement methods itself, but we can also develop the full hardware from the sensors, the measurement hardware itself, the data processing, the signal processing, energy supply, and finally the integration up to the standardization, so that you can completely integrate a tailored monitoring system into the application. Again, with some colorful figures, the full value chain that we can offer in developing systems for monitoring and testing. We develop simulation tools, we do simulations, we develop the method itself, the data analysis, the signal processing. We can develop the sensors, ultrasonic sensors, and monitoring transducers. We develop the electronics, the software, and we finally embed it into your applications, as you can see here in the wheel shaft of a high-speed railway in Germany. And this is what we can offer. Finally, we are not limited to any application. So we work for all fields of application, from energy sector, from renewable energies like wind energy turbines, onshore and offshore, beginning from the foundation, the ground connection for offshore structures. The ground connection is here, this joint between the rotor blade or the tower and the foundation underwater, up to the rotor blade, made of glass fiber or carbon fiber, or a sandwich between glass and carbon fiber. We work for energy sector power plants, monitoring pipelines, monitoring high temperature pipelines up to let's say 300 or 450 degrees Celsius, monitoring vessels, storage vessels made of metal or made of composite, made of carbon fiber for high pressure applications like storing hydrogen. And we can also develop systems for monitoring composites in the aerospace and aviation sector, in the automotive industry, up to the development of systems that can monitor production processes. Like this example here, this is a chocolate, and here our customer wanted to monitor its packaging process to identify the position in the packaging machine where most of these chocolate sticks broke during the packaging process. And there we've implemented an accelerometer sensor to monitor the forces acting in the packaging process. It was a really nice project because we got a lot of chocolate out of these experiments. But again, to summarize, we are not limited to any kind of applications. We work on all different fields, and we have the possibilities to adapt our hardware, because this is the foundation of our hardware, measurement hardware, sensor nodes, communication protocols, and so on. Yeah, as mentioned in the headline of the seminar today, I want to talk about guided waves. Guided waves are a special type of ultrasonic waves. Of course, we can use a lot of other techniques. If we talk about ultrasonic techniques, then maybe you know the classical NDT phased array testing, which is a manual testing done by people on site. And also eddy current, the electromagnetic testing is possible as non-destructive testing, as well as optical methods like OCT. We want to focus on electrodynamic vibrations or electrodynamic waves, and especially on guided waves, plus minus some kilohertz. Maybe in the next slide I can show you the differences more precisely. If we talk about monitoring of vibrations or elastic motions, then we have the low frequency movement, which is in the range of several hertz to several kilohertz. Usually we talk about vibration measurements or modal analysis. This means we measure the shape of the vibration of structures, and if, for example, this modal shape of a structure changes, then we know there's a change in the structure. The defect resolution is really low because we just get information, okay, there is something wrong in our structure. But this is, for example, a useful tool for monitoring infrastructure like buildings or bridges. I don't know if you know, but 10 months ago, there was a bridge collapse here in Dresden. And for example, for monitoring this critical infrastructure or this civil infrastructure, modal analysis is a useful tool. On the other side, the high performance NDT, like phased array testing or ultrasonic testing, this uses really, really high frequencies. By using really high frequencies, you can get really, really detailed information about damages up to the micro and nanometer scale. But this is a testing method that has to be done automatically, manually. You have to take your sensor probe, your ultrasonic probe. You have to go to your specimen. You have to test it manually, and then you have to move your sensor head, your probe, from position to position. But in the end, you will get a really detailed view into your structure. And in between, there is the technique of guided waves. Guided waves are in the range of several kilohertz. I would say some 100 kilohertz, 100 to maybe 500 kilohertz. As you can see on this scale, of course, the defect resolution is a little bit limited or smaller, of course, than the highly detailed NDT techniques, but much better than only vibration analysis. The distribution of the sensors depends a little bit on the material, but as you can see here in the examples, and I have more detailed slides later on, you can monitor structures with a length of 40, 60, 100 meters. This is a rotor blade with a length of 40 meters, and we've also investigated rotor blades with a length of more than 100 meters. The same for pipelines. You can also monitor pipelines with more than 50 meters by using guided wave techniques if you have good transducers. Yeah, to get an impression, what are guided waves? The easiest case is imagine you drop a stone into the water. If you drop a stone into water, then you will get surface waves. Yeah, these surface waves propagate because you have a difference in the mechanical stress between the water and the air. And now if you have in your structure a second surface, for example, if you investigate a pipeline or a vessel, a storage vessel, then you have two surfaces really close to each other. And then if you excite vibrations or a wave into the structure, then these two surface waves, they overlap and are guided by these two surfaces. And this is why it is called guided wave. These are ultrasonic waves guided between the surfaces, guided by your structure, and propagating through the structure, even through curved structures or really complex structures, through heterogeneous materials, through anisotropic materials. And in applications, really often piezoelectric transducers are used because they can excite and receive these waves, and they can be in really many cases embedded really easily into or on your structure. To get an impression, I have this animation here where you can see the displacement of your particles, of your molecules in a wall cross section. So this is a cross section of a wall. This could be a pipeline or a pressure vessel or whatever. And then we are talking about different modes, because in a 3D space, we are all living in a 3D space. In a 3D space, you have three directions of displacement, two in plane and one out of plane. And due to these three spaces, one can say one have different modes of propagation of these waves. One special feature of these waves is, on the one hand, some of them are symmetric. Symmetric means symmetric to the center line of your cross section, which is here, this example here, the center, or antisymmetric. And therefore, one can call them S modes or A modes, symmetric modes or antisymmetric modes. And they have also different properties. So these modes propagate with different velocities, and these velocities depend on the frequency. You can imagine that you have a relationship between wall thickness and wavelength of your wave. And this relationship between wavelength and cross-section or thickness of your wall leads to different velocities depending on the frequency. And this relationship is can be calculated analytically or numerically, and then can be displayed in so-called dispersion diagrams. In these diagrams, one can see the velocity of the different modes, symmetric or antisymmetric modes, depending on the frequency and the thickness of your structure. In an example later, I will show you how we can use these relationships to build a really easy monitoring system. But first of all, I want to present two different types of techniques how to use these guided waves for monitoring. First of all, monitoring means we install our sensors permanently on the structure. It is not intended to use it as a manual inspection system. It is, one use it as a permanently installed system. I would compare it with a smartwatch. So maybe everyone has an Apple Watch or Samsung Watch or whatever, a smartwatch, measuring some parameters from your daily life. For example, your steps or your pulse, or I don't know what else. My smartwatch can measure a lot of other information. And this is an easy example how you can imagine we want to install sensors permanently on a structure, measuring data and get information out of this data. And the data that we measure are elastic waves, acoustical waves. And one example or one possibility to do so is the so-called acoustic emission. Acoustic emission is a passive method. That means we install a network of sensors on our structure. In this example, it is a rotor blade from a wind energy turbine. And all these sensors are permanently listening to the structure. They are listening to acoustical events. And an acoustical event, for example, could be a crack or a damage occurring in your structure. And the crack, you can imagine, makes noise, makes a sound, makes an acoustical emission, an acoustical signal, and this signal propagates as acoustical waves in your structure, is measured by your sensor system, and then by analyzing the data, one can get information out of it. One can localize the position of the damage by analyzing the signals, for example, in frequency or amplitude or duration. One can also get information about the type of damage. So especially in composites, different damage like delaminations or debonding, they have different features in frequency domain and in the amplitude. So to say, different damage, they make different noises, and this can be identified by your system. We use this technique, the so-called acoustic emission technique, for monitoring a lot of different applications and examples. You can, for example, investigate or monitor the growing of defects. For example, if a delamination increases from time to time, it can be done in operation of your systems. There's no need to stop your system until you will get information that, okay, there's a critical damage. And we've done this for, this is an example of a wheel made of CFRP in the automotive sector. This is a pipeline, a high temperature pipeline in a power plant. Here on the right side, this is a frame from a railway wagon, also made of CFRP. And again, here you can see on the right top side the rotor blade with some first results. I will show you the meaning of these colorful dots in a few seconds. Just to get an idea how we install these systems on the example of this rotor blade, of course, the sensors are attached inside the rotor blade. So they are protected against impacts from the outside and also against environmental conditions like rain, snow, etc. And the measurement device itself is also installed in the rotor blade or in the cabin on top of the tower. And here on the one hand, we've investigated rotor blades on a test bench, but also in field with for a repaired rotor blade to monitor this repaired spot if the position or this location with the repair patch remains in operation. How do we get information what type of damage we have? Well, usually we start with coupon tests. in this example here, we have done tensile tests on coupon samples made of the same material as the rotor blades, and then by destroying these coupon tests, we collect the acoustical data and analyze the damage. And with using these coupon tests, we will get the database for these materials or for these specimens, for these rotor blades, where we can see clusters in the frequency power domain. Power here is like the amplitude or the energy in your signal. And these clusters will help us in identifying the type of damage in the rotor blade later, in operation. Of course, we need the kind of training data for the system, and these training data is usually generated by coupon tests in the lab. But to show that it also works for more complex geometries, I want to show the results from the development phase of this railway application here. So this is a railway made of carbon fiber, and also here this axis or this frame is made of carbon fiber. And during the development of this frame, our customer wanted to compare FEM simulations, so finite element simulations, with bending tests. In this example, we've installed acoustic emission sensors. You can see here these red dots. These are the acoustical sensors attached or clamped to the structure. And you can see the bending test. And during fatigue tests, or during these fatigue tests, we've done acoustical emission. So this means we've listened to the structure. And what you can get is, in the easiest case, a plot of localized acoustical events. Here you can see the geometry from the CAD model, and the colorful dots are the number of acoustical events coming from these positions. And here on the left side, or maybe a little bit too small for you, but I can tell you the number. You can see the number of load cycles. So starting from 0 or 1 million to 2 to 3 million. So it was a fatigue test. Means we have a lot of bending tests there. And what you can later see is the accumulation of the acoustical events in some areas. You can also slightly assume even fiber bundles where a fiber breakage started. And you can also see areas where a denomination made a lot of noise. And this information you can later use to compare your design from the finite element model with the real life bending tests. And you can identify the weak spots in your structure. You can identify the spots in your structure that may fail after time, after what is it here? 12 million load cycles. So this is a monitoring technique for, of course, in-field testing, but also supporting other steps of the development of products, like in this case, the design phase of the product. Yeah, this is an example for acoustic emission, and another technique using guided waves is the so-called acousto-ultrasonic technique. We call it an active method because we actively excite guided waves into the structure. In general, one can use the same piezoelectric transducers because they are able to excite and to receive signals. And if we have, again, a distributed network, then we can do both. This example here is a pipeline construction. You can see these two belts. This is one prototype of our sensor belt. And here are piezoelectric transducers embedded, and these transducers can excite guided waves into your structure. One transducer excites the wave, all other receive the signals, and then in a round-robin manner, the next transducer excites a wave, and all the other transducers collect them. And so you have a network from between all combinations between all transducers, and you can store these signals into a database. Let's say this is the blue curves stored into a database. If you repeat this measurement, if you actively start this measurement again later, 1 day later, 1 week later, 1 year later, and in the time between the measurements there was a damage, then again the wave propagates coming from the transducers, but then you will get reflections or a scattering of your wave coming from this damage, and this will change the received signals. By analyzing all these signals, and here you can see we have 2 sensor belts with a lot of different transducers. By using all of this information and more detailed signal processing, you can get really detailed information about damage positions. In this example, it was an artificial crack, a cut into the welding of this metal pipeline structure. This technique also works for composites. In this figure here, let me show you the same idea. We have a CFRP component. We have a sensor system or a measurement system connected to transducers, and then the system excites a wave. This wave propagates in your structure and is collected by other transducers and stored in a database. If you have a damage in your structure, a delamination or a crack or fiber breakage, then the next measurement that you've started will show you again differences in the signals. And again, this can be used to analyze for the position and the type and in the best case also the size of your damage. Especially for carbon fiber or glass fiber, this is a really useful tool because you can monitor for non-visible damage. I think you know that in composites and carbon fiber, damage can be under the surface where you cannot see the impact, for example, but can be really, really dangerous. And these waves, as you've seen, they propagate into full cross-section of your structure, can be used to monitor non-visible damage or not visible from the outside, from the surface, into really complex structures. I want to start with an easy example for using this technique for monitoring pipelines. Pipelines under isolation in the best case for high temperature pipelines. But this is a really easy example for monitoring corrosion or corrosion in pipelines. If you remember, we have a relationship between frequency and wall thickness and velocity of the waves. And you can fix the frequency because this is a parameter in your setup and your hardware. You can fix the distance between your sensors. And then if you just measure the time of flight between 2 sensors, you can measure the velocity of the wave between these 2 sensors. And by using the relationship between velocity, frequency, and wall thickness, you can recalculate the wall thickness of your pipe in the section between your sensors. So this is the easiest case of a sensor system. Different sensors, a measurement hardware, and then a monitoring zone, a zone that is monitored for corrosion. As you can see, it can be also under isolation because the transducers are really thin in the best case, but we can also use different techniques. And then if we can go into the dispersion diagrams, as you've seen them on the previous slides, then we just measure the propagation velocity between the sensor positions, and we recalculate the average thickness of the wall of your pipeline between these 2 sensor positions. This is the easiest case by just using 2 sensors. As you've seen, if we have more sensors, then we can get more information. But even this easy system, only 2 sensors and 1 measurement box, can monitor your pipelines permanently for corrosion, especially in critical areas. And one big advantage is you can put these sensors on positions where you have access to, And you can monitor areas where you do not have access to, for example, elbows in a really complicated structure, or again, in power plants under isolation. And as you've seen in the example with the offshore sensor belt, if we have more sensors, we can get more detailed information about the structure. Our idea here is to monitor offshore structures like these jackets. This is a possible foundation for wind energy rotor blades, as you can see on the picture on the left side, but also for other pipeline structures underwater. This is a really harsh environment. At the moment, this is done by divers, but as you can imagine, due to the environmental conditions, the divers or the measurements done by divers are limited. And the idea to use remotely operating vehicles, ROVs, for investigating these structures is, I think, a much better one. Here on the right side, you can see the COMO belt, which is the sensor belt with embedded transducers, embedded electronics, and embedded power supply. And this was tested offshore in one of our labs in the Baltic Sea in the north of Germany. We have a lab for testing offshore equipment. And as you can see on the right side, this is an example where we used two sensor belts. You've seen this example in the previous slides. And by using, it's a kind of tomography, as the doctor does if you go to X-ray tomography. The main signal processing idea, the main algorithm is the same, and this can give you a really quantitative information about damage positions and damage sizes. Of course, you need some more sensors than only two, but it can give you really, really detailed information about this. Yeah, one really interesting question is, okay, we are talking about work underwater, and water is, of course, a damping material. So what about the range of these guided waves? The extreme case, we've tested these techniques for monitoring the grouts. The grouts is the joint between the tower of the wind turbine and the foundation. The foundation is a so-called monopile, which is a pipe or a cylinder, a pipe with a diameter of 6 meters, a wall thickness of 6 to 8 centimeters underwater, and a length of 40 meters or 80 meters, depending how long or how deep the water is. And we've installed one of these sensor belts some years ago in the Baltic Sea in Germany. The divers supported our team by installing the sensor sleeve underwater. And on the platform here, on the access point to the turbine blade, we've installed an piezoelectric transducer. Here you can see the figure of the installation. So you can see the diver installing the sensor belt underwater. And above the water, in the access area of the platform, we've installed this piezoelectric transducer. Of course, it is a powerful one, but we were able to propagate waves over more than 10 meters in joint pipeline, or let's say joint pipes. So the tower itself is also like a big pipe, or this transition platform is also like a big cylinder with a diameter of approximately 6 meters, as you can see here. We have 8.5 meters of grouted joint, which is the area of grout and the connection between these two pipelines. And then 1 meter from this transition area, we've installed the sensor belt with 32 sensors. So this is maybe, let's say, the extreme case for using guided waves, but we were able to measure guided waves with the sensor belt underwater. So if by using an installed transducer in the access area of the monopile, and by using the sensor belt underwater, we are able to monitor this joint connection between tower and monopile. This is a real measurement signal from the offshore measurements. we have the calculated first arrival. So this is the point where we approximately assume that the first wave package will arrive. We got this information out of the dispersion curves, and here you can see in perfect agreement the arrival of the so-called A0 mode, which is in totally agreement with the calculated theoretical value. Yeah, this is the extreme case for monitoring with guided waves, but our vision here is to have fully automatically working robot ROV for monitoring these structures underwater. This robot itself can supply the COMO belts, the sensor belts with energy, collecting data and analyzing all the data. So this is the vision, and we are on a good way because we've already installed some of these belts offshore and tested them offshore. Yeah, now let's come to complex structures like anisotropic materials, like carbon fiber structures, for example, for high pressure storage of hydrogen. Really often the needs are driven by accidents. In this case, it was a natural gas powered car with an explosion after a parking accident. This becomes more and more dangerous because the pressure of hydrogen pressure vessels are now up to 700 bar, so not only 550 bar, but 700 bar. And of course, a failure or an accident may cause definitely not only expensive damage, but also risks human life if one of these cars explode. Therefore, we can also use guided waves. Same idea, we embed transducers into the structure. We measure with guided waves with a distributed sensor network. And as you've seen in the previous slides, maybe the same story again, we compare the signals between the undamaged state after installation of the vessel and the damaged condition or the current condition after a damage, and then we can also localize and visualize damaged positions. This can be done for pressure vessels, but also can be embedded into really thin structures, like for example here, again, a stiffener structure in electrical cars. And let me show you the next slide where we have embedded this into racing cars here. A comparable idea to the sensor belt. Transducers and electronics are embedded into the structure, and the measurement hardware is external, in this case in the repair shop for the cars. In the offshore application, it's the ROV where all of the hardware is embedded, and you only bring the sensors and the electronics to your structure. But whatever is needed, if the hardware is also needed on site, then of course the hardware can also embed it, but maybe not in the car. What we usually do, or what I usually do, is designing the sensor systems. The main question is really often, how many sensors do I need and where do I have to put these sensors? And this is in our department really often done with simulations. So we start with the real world component. We build a CAD model, a digital twin of the structure, and then we simulate the propagation of the guided waves in these structures, even in anisotropic carbon fiber and complex structures. And then by using tools, so-called probability of detection tools, POD, we analyze different spots in the structure for damage sizes that can be detected with a defined probability. And of course, really often we need the specifications from the owner or from the developer of the specimen. So the owner or the designer of the specimen has to say, okay, a damage of this and this size is critical. And then we design the sensor system in a way that these critical damages can be detected with a probability of 90%, 95%, or even more if needed. And this gives finally the design of the sensor network, the positions of the sensors, and also the number of the sensors. So this is really often done with simulations. Last example for using guided waves, from my point of view, interesting example, maybe that you've not have in mind, is, for example, also monitoring batteries. In the case of lithium-ion batteries, if you charge and discharge the battery packs, for example, in electrical cars, so all of the electrical cars, they have lithium-ion batteries inside. The elastic properties of the battery changes between charging and discharging, namely the density, the Young's modulus, and these changes in the material has also an effect to our guided waves. So same idea, by installing piezoelectric transducers, batteries, you can measure the charging and discharging process. You can precisely measure the state of charge, which is really important for electrical cars, that you know the remaining distance that you can travel with your car. But you can also measure the state of health. So how good is your battery after 100 or thousands of charging cycles? This is what we've already tested and published. And this is, I think, a really new and interesting idea to using guided waves, because this is a really unusual application far away from pipelines and composites. Last but not least, I want to show you how to cooperate with us if you are interested in doing research with Fraunhofer. The easiest case is a direct quote, so that you order R&D services in our house. First of all, we write a quote, but then you order directly develop R&D services in our house. We can also do joint R&D projects, public funded projects or governmental funded projects. And last but not least, we are interested in bringing the technology into the market by licensing or founding spin-offs. And one example is our latest spin-off from our department is the company Acoustic, which is a company now in Norway developing a non-contact system for level measurement in oil and gas separators and oil and gas applications, measuring the level of solids, water, emulsion, oil, and maybe foam in oil and gas separators from the outside with a non-contact system. Yeah, so I'm exactly in time. So Lina said I have time until 12:50. Feel free to get in contact with me if you have further questions or if you want to get into discussions. And now we have 10 minutes for questions if you're interested in and if you have questions. Thank you.
Yeah, thank you, Dr. Kilian. It's really interesting and impressive, especially for the final application for the battery monitoring using guided waves. This is the first time I see for such a application. We never saw think about that. It's really good. Thank you. So we start the stage for questions. I saw in the Q&A panel there is one question from Asif. So I have allowed Asif to talk. So Asif, you can just talk directly.
Okay. So thank you, Kilian, for the very interesting talk on the guided waves. So you may be aware, in the oil and gas industry, we usually are interested in the condition monitoring of critical, more thicker adhesive joints. So where the two parts that we join together have a thickness of around 6 millimeter. And when we join them together adhesively because they are non-metallic, so we cannot weld them together. So we also have high damping adhesive material in between.
Yes.
So based on your experience, can we come up with a guided wave system with less attenuation? And also just to give you an idea, in the oil and gas industry, the quality of the composite are much more lower compared to the aerospace, and I believe even in the windmills. So So based on your experience, how would you suggest to go for the guided wave system for such a high dispersive and highly damping system with very larger thickness compared to the example that we just saw?
Yeah, maybe if I go back to the example of the rotor blade, I think this is an even worse example. So the rotor blades are manufactured of glass fiber and nowadays also glass fiber and carbon fiber. Oh, a lot of slides. And they have a thickness from up 5 to 6 centimeters. They are really heterogeneous and anisotropic. And even in these structures, we can measure with guided waves. Of course, this is also really highly damping material. Let's say in general, then we have a sensor every 1 meter. But we can measure in even these materials over a range of more than 1 meter. And so regarding your case, I think from my point of view would be possible by choosing the correct transducers, of course. We need transducers with enough power to excite the waves. And on the other hand, as you see, we have 3 different wave modes. I could imagine that in oil and gas industry, it means in the inside, there's a media also damping the propagation of your wave. But this is the same example as offshore, where we have the media, the water outside of our pipe. And by using a special kind, the shear waves, a special kind of guided waves, they are not influenced by the media outside of your structure. So they are not influenced by the damping and are, for example, in our case, used for the offshore monitoring. So long story short, I think if you are interested in, and if we can talk about more detail about your application, then I think we can find a way to use guided waves for this application.
Okay, that would be very interesting. Just a quick follow-up on that one. So you mentioned we have to permanently attach these guided wave sensors. Piezoelectric patches are those very interesting builds that you just shown in some of the examples. But in the oil and gas field, we have hundreds of these joints. And upon installation, for example, we want to go for a quick quality assurance. So is it also possible to quickly attach somehow and then check the quality, detach it, move it to the other joint? Because installing on hundred of joints would not be a practical solution.
Yes, in general, this is possible. Let's say our department here is focused on permanently installed sensor systems. On the other hand, we also have a department developing NDT equipment. As you've mentioned, you have your device, you go to your spot to be inspected, put your device on it and get information about the condition of, and then go to the next spot. This is only the focus of my department. Of course, we have colleagues doing the same stuff for NDT techniques as you want to have it. And then in the collaboration, of course, we can use the same physical idea using guided waves combined with the possibility to have a transportable measuring device.
Thank you. Thank you.
You're
Hope
welcome.
to have a collaboration on this one. Yeah.
Yep.
Thank you. So there is another question from Audi. Audi, you can talk.
Okay, thank you, Sheldon. Thank you, Dr. Kilian, for the very interesting presentation. I have a question regarding the compensation of environmental effects, because I see that you do a lot of outdoor things like wind turbines, maybe batteries that, you know, have environment like temperature differences, etc. Do you have to compensate for that in any way?
Yes, yes. This is really often a part of our signal processing. First step is really often filtering. For example, for rotor blades, you do not want to monitor rain. Raindrops also makes noise on the rotor blade. For example, this is an environmental condition that you have to filter in your signal. And again, yeah, temperature, that's right. Temperature compensation is part of our signal processing, and other conditions as well, depending on the application. Could be, for example, also the pressure. If you have a pipeline or a vessel that is refilled, then you also have changing pressures, which could be also a condition that changes your signals. This is also part of the signal processing. Yes, you have to do this.
Thank you very much. If I can follow up on that, does that mean that you have to also simulate that when you want to develop the system?
Yes, we try to. Yes. Depends a little bit because really often for simulation you need really good material parameters, and these material parameters are not really often available for different temperatures and different conditions. So then you just have an assumption. This is also an example where we, in the best case, have the possibility to do coupon tests with smaller test specimen, where we can model the behavior in a lab environment much better than in simulations where we do not have the correct input parameters. But depends on the material and the application.
Okay, thank you very much.
You're welcome.
Thank you, Dr. Kilian. So I don't really see anyone have questions. So I have one last question about the active guided waves. Because I see that you're Fraunhofer of investigating the passive, like active guided waves. So do you does Fraunhofer explore the passive guided wave? For example, when we start up the system of pipeline, there will be definitely vibrations and activated guide waves. So do you think this can be used for some signals, and we just receive all of this signal to detect the crack or any defect?
Yes, yes. So the backbone of our hardware is so-called Como base, which is the base hardware for all of our systems. This is a system that can measure actively and passively. So this is one hardware for doing acousto-ultrasonic active measurements and acoustic emission with the same hardware. And for example, as I've mentioned, we had a bridge collapse here in Dresden, and now we're developing an acoustic emission system, especially for this case of monitoring civil infrastructure, monitoring really low frequency vibrations and really low frequency acoustical signals in really big bridges. And this is exactly what our hardware can give you, the possibility to do both passive measurements and active measurements. So this is maybe one of our main competences, this hardware and the center of all of our developments.
Yeah, I see. So this Como belt is still under development, or it's already available in the market?
It is not available on the market because we are not a company. We are not allowed to sell it onto the market. We have this standard Como belt, and then we adapt it for the needs of our customers, and then we can transfer to our customers. So it is still under development for new needs, and it is not yet on the market because we as non-profit, we are not allowed to bring it into the market. We just have the standard lab equipment, and then we have to adapt it for the needs of our customers.
I see. I think that's all from my side. And thank you, Dr. Kilian. This presentation is really informative, really insightful. So thank you, Dr. Kilian, and everyone attending this seminar. We look forward to seeing you for next seminar. I think we can close it.
Thank you very much. Have a nice
Thank you.
afternoon.
Thank you. Thank you,
Bye.
Kilian. Bye. Bye-bye.